and Yehudayev, who studied these quantitative Sylvester-Gallai theorems. These were then quantitatively improved in joint work with Dirac and Wigderson, and they are very intimately connected to the question of two-query locally correctable codes of the reals. In joint work with Albert I, Zevdvir, and Avi, we also study approximate or stable Sylvester-Gallai-like theorems, and I'll mention this. And much of the talk, I'll be talking about a very recent work with Dwyer and Wigderson on some combination of high-dimensional and quantitative Sylvester-Gallai theorems, which are connected to three-query locally correctable codes over the reals. And that would be the significant bulk of the talk. So here's the plan. In the first half, I'll tell you about all these extensions of the Sylvester-Gallai-like theorems which are known. And in the second half, I'll tell you what the connection to locally correctable codes is, and then this new lower bound for three-query locally correctable codes over the reals, which we get by studying the three-query version of the Sylvester-Gallai theorem. Okay, so first the Sylvester-Gallai theorem I talked about, the proof was very specific to the real numbers. We use a lot of properties of the real numbers to prove the theorem. For instance, the notion of distance between the point and the line. Also, the fact that two of the points were in the same side of the foot of the perpendicular. So the ordering of the real numbers was very important. And it turns out that the Sylvester-Gallai theorem is in fact not true over the complex numbers. So there is a configuration of points in the two-dimensional complex plane where the points are not collinear, and the complex line through every pair of points passes through the third point. So it turns out to be not true, but it was shown by Kelly that you can't have such configurations in three-dimensional complex plane. So if you have a finite set of points in some complex space where the line through every pair of points passes through the third, then these must be contained within a two-dimensional plane. You can't have a higher dimensional configurations. And the original proof was fairly complicated. In 2006, the first elementary proof of this result was given. And in some of what I'm going to be talking about later, the tools we develop will give a new proof of this result using some basic linear algebra. So that's that's Sylvester-Gallai theorem over the complexes. Here is another very interesting version of the Sylvester-Gallai theorem, the quantitative Sylvester-Gallai theorem, where we don't ask that for every pair of points the line through them passes through the third, but for many pairs of points you have the property that the line through them passes through a third point. Can you then say anything about the structure of the points? Okay, so here is I'll say a configuration of points is a delta Sylvester-Gallai configuration. If for every point there are many other points, so delta fraction of other points, so that the line through those pair of points passes through a third point. So for instance, a grid is, I think, a 1/4 Sylvester-Gallai configuration. So for every pair of points, there are many other points which says that the line through them will pass through a third point. And so this was the setting which was studied in the work by Barak, Wigderson, and Yehudayev. And this was a very beautiful result, very beautiful techniques, and I'll talk a little bit about this result. What they showed was, if you take any delta Sylvester-Gallai configuration in some Euclidean space, the only way such a configuration can exist is that the dimension is bounded. It's at most some constant depending only on delta. It's order of 1 over delta square. And then in joint work with Dwyer and Wigderson, we analyzed their proof more carefully, and we were able to show that in fact the dimension is at most order 1 over delta, and this bound is tight. Okay, so for instance, if you take 1 over delta skew lines, each containing delta n points, then it would form a delta Sylvester-Gallai configuration in 1 over delta dimensions. So we almost fully understand how such configurations, the parameters for such configurations. Okay, so let me say a few words about the proof of this result, because many of the other Sylvester-Gallai-like theorems, even the Sylvester-Gallai for the complexes, etc., follows basically this outline of proof. the proofs of these incidence theorems is going to follow from something called the rank bounds for design matrices. So let me tell you what the connection is. And I'm just going to give you a very high level outline of proof and not go into details. Okay, so suppose you have a bunch of vectors v1 through vn in some complex space, and you have, it's a delta Sylvester-Gallai configuration. So you have a whole bunch of collinear triples within your set of points. So for every collinear triple, these 3 points are going to be linearly dependent. So there are some coefficients alpha I. So for every vi, vj, vk, there will be some coefficients alpha I, alpha j, alpha k, so that the corresponding linear combination is 0. And you can use all these dependent triples to construct these two matrices, V and A. V is the matrix where you just put all the vectors Vi as the rows of the matrix, and A is a matrix where you put, for the rows of the matrix, you put these triples alpha I, alpha j, alpha k in the I, j, kth location. Good. Then it's not hard to see that if you construct these matrices, A times V equals 0. Okay, so V was the matrix of all the vectors. A was the matrix you got by just for every collinear triple you added the corresponding linear combination as a row of the matrix. So we were given the set of vectors which formed a delta Sylvester-Gallai configuration. We built this matrix such that A times V is 0, and then carefully understanding the matrix A and carefully pruning it, it was observed that this matrix is actually a design matrix. And I'll say what I mean by a design matrix. But this matrix was a design matrix. What the goal of the theorem was to prove that the vectors V are low dimensional. Right? So the goal was to show that the vectors are low dimensional. This is equivalent to saying that the rank of V is small. So you want to prove the rank of V is small. What you know is A times V is 0. So one way to prove that the rank of V is small is to prove that the rank of A must be really large. If the rank of A is really large and A times V is 0, the only way it could be is that the rank of V is small. That's the proof strategy. We got this matrix A, it was a design matrix, and now it just suffices to lower bound the rank of this design matrix. So let me tell you what a design matrix is. We say an M by N matrix is a QKT design if you just look at the zero non-zero pattern of the entries of the matrix. Every column has many non-zero entries. The intersection of every pair of columns has a small intersection, and every row has few non-zero entries. Though this every row has few non-zero entries is not such an important term, the K and the T are really the important parameters in the setting. So every column has many non-zeros, and the intersection of every pair of columns is small. The support of the intersection is small. That's what a design matrix is. And Barak, Virvigdason, and Yehuda showed that any such QKT design matrix must have large rank. And in joint work with Virvigdason, we improved the bounds for the design matrices, and this bound we get here is basically optimal. So basically every QKT design matrix, so having entries over the complex numbers, if it is a QKT design, its rank is at least so much. And in the setting where they showed up in the Sylvester-Gallai configurations, Q was basically a constant, T was basically a constant, and K was order n. So this term ended up being a constant. So the rank of the design matrix was basically full rank. It was n minus a constant, which tells you that the corresponding matrix V, the vectors of the Sylvester-Gallai configuration had to be in constant dimensions. Okay, so that's how it worked. I won't tell you what goes into how these rank bounds for design matrices are proved, but the main idea was some notion of matrix scaling, which was a very, very nice idea and very beautifully used. So some things to note about the rank bounds. These hold for any field of characteristic 0 or very large characteristic, but they are not true over small finite fields. So they are counterexamples to this result. And yeah, just this rank bound result, this statement about the rank bound itself is enough to imply the Sylvester-Gallai theorem over the complex numbers. So it gives you exactly the constant 2, which was needed for the dimension of Sylvester-Gallai configurations over the complexes. So let me tell you another, so that was the quantitative Sylvester-Gallai theorem. Let me tell you another variation which you can ask of the Sylvester-Gallai theorem, which is the stable version of the theorem. So you have a bunch of points in Euclidean space, and suppose you know that for every pair of points, the line through that pair almost passes through a third point. So these points are not exactly collinear, but approximately collinear. What can you say about this configuration of points, where every pair of the line through every pair is approximately passing through the third? So a natural thing to hope for in this case would be to say the points are not, you can't perhaps hope to say that they are all in low dimensions, but you could perhaps hope to say that they are approximately low dimensional. So the hope could be that then all these points must be close to linear, close to lying on a line. So it turns out that the statement, at least as I stated it, is not quite true. So it's not true that, so there is a configuration of points robustly spanning a high dimensional space, so that for every pair of points, if you draw the line through them, that line will be epsilon close to a third point. You can actually find such a configuration which is high dimensional. So this stable Sylvester-Gallai theorem as is not true. To make it true, perhaps more assumptions on the set of points might be necessary. And what we showed with Albert I and Dwyer and Wigderson is that suppose you add the assumption that the distances between pairs of points isn't too skewed. So all the distances are bounded between 1 and some parameter b. Then, and you know that for every pair of points there's a third point which is epsilon collinear with it, then the set of points is going to be pretty close to a space of dimension b to the 6.
Are there examples of these that do not come from just perturbing genuine Sylvester-Gallai examples?
Yes, so this counter example which I said, which I talked about, where these...
In the balance setting.
In the balance setting, we know very, very few examples of how, so I don't know any non-trivial examples.
So it could be the case that all such sets are in fact just slight perturbations of genuine coordinates.
Absolutely, yes. So this bound we show is actually probably far from tight, and perhaps you can put much milder restrictions on the set of points and conclude truly that the only way you can derive is from genuine Sylvester-Gallai configurations, and we don't know how to show this. And I think it would be very, very interesting to show such a result, and these results are also very closely connected to other questions in combinatorics, which I don't want to talk about, but I think that's a very nice direction to pursue.
So epsilon prime dimension means what exactly that you can...
Epsilon prime is, so I don't remember what we show, but epsilon prime was some function of epsilon.
You asked about the definition of this.
Oh, sorry. So all these points are epsilon prime close to a subspace of dimension b to the 6, and where the constant epsilon prime is some function of epsilon. So that's one kind of proof. The way we prove this result at a high level follows a similar outline to the old proof I talked about, where we construct this design matrix. But now we don't get to just lower bound the rank of the matrix. We need to robustly lower bound the rank of the matrix, where we show that the number of eigenvalues with eigenvectors with small eigenvalue are large. Okay, here's another variation of the Sylvester-Gallai theorem, which is very interesting also. So far we just talked about incidences between points and lines. You can talk about incidences between higher dimensional planes and points. So the Sylvester-Gallai theorem says that if for every pair of points the line through them passes through the third, then the points must be low dimensional. you can ask, what if through every set of k points, the plane through them passes through a k plus first point? Can you then say something about the dimension of these points? And such high-dimensional Sylvester-Gallai theorems were studied a long time ago, and over the reals we have pretty good bounds, which say that if you have this k-dimensional version of the Sylvester-Gallai theorem, the points must be in at most 2k dimensions. The work by Baragdwil, Vigdis, and Yehudeov. So this result it's elementary, but the proof is still fairly complicated. The techniques introduced in the rank-bound kind of techniques are robust enough that they extend to prove such results even over the complex numbers. I know they also give quantitative versions of these theorems over the complex numbers, but the bounds are still far from from optimal. So that's the high-dimensional Sylvester-Gallai theorems. There was even you can ask colorful versions of these theorems, and this was something we used to understand the structure of arithmetic circuits. This was the kind of question which came up, where the setting was you have a finite set of points in Euclidean space, and each point was colored one of k colors, if the hyperplane if for every k minus 1 points of different colors, if you look at the hyperplane through them and it passes through a point of the kth color, then the points need to be low dimensional. This was studied by Edelstein and Kelly in the 66. They did it for k equal to 3, and we had to generalize similar results for general k, and this showed up in arithmetic complexity. So that was, again, one kind of Sylvester-Gallai theorem. And I just want to mention one more. So Ben Green and Terry Tao very recently studied another setting of the quantitative Sylvester-Gallai theorem. So the usual Sylvester-Gallai theorem, the way I said it, was that if you have a set of points spanning two-dimensional space, then you must have at least one line which passes through 2 points, exactly 2 points. But maybe there are many lines which must pass through exactly 2 points. And so this was an open conjecture for a long time that you must have at least n over 2 such lines which pass through exactly 2 points. And this was fully resolved in this recent work using some very beautiful techniques. And this work actually fully characterized how these configurations of points must look like, which have very few lines, ordinary lines, which are lines through exactly 2 points.
This is for n bigger than 10 to the 10th.
So this result is known for some very large values of n and still open for some small finite values of n. Okay, good. So that's what I wanted to tell you about the kinds of Sylvester-Gallai theorems that we've been looking at recently. In the next half, let me tell you what the connection of all these Sylvester-Gallai theorems is to locally correctable codes, and then tell you about 3-query locally correctable codes and what we can do for it. So a locally correctable code, a linear locally correctable code, is given by the generator matrix. And you have some message m, and the encoding of the message is just m times g. So it's some k symbol long message gets stretched to some n symbol long vector, and then some corruptions occur. So some delta fraction of the coordinates gets adversarially corrupted, and so what you get after the corruptions is some corrupted code word. And in the usual notion of error correction, you would want to take this corrupted code word and recover what the true uncorrupted message is, or the true uncorrupted code word is. In a locally correctable code, you want something much stronger. You want to recover every symbol of the true code word by actually looking at only very, very few locations of the corrupted code word. So we'll say a locally correctable code is a Q delta locally correctable code, and think of Q to be something like 2 or 3 for now. If whenever you corrupt delta fraction of the locations of the true code word, you can recover any coordinate of the true code word accurately with high probability by looking at the corrupted code word only in Q locations, where Q is something really small. So for instance, this is the way how the decoder would work. You would feed it, you would say, okay, I want the ith symbol of the true code word. The decoder would then just go query the corrupted code word in some very few locations and tell you what the ith code, the true ith symbol is. And here's an observation which is a fairly straightforward observation. So suppose you wanted the ith location of the code word, and the decoder queried the j and k and lth locations to tell you what the value was at the ith location. The only way the j, k and lth locations can tell you what the value of the ith location is that if you look at the corresponding columns of this generator matrix, they must be linearly dependent. So pi, pj, so here q is 3 in this example, so it must be that pi is in the linear span of pj, pk and pl. And in fact, since this decoder needs to be able to give the correct answer with high probability, even if there are corruptions, the only way this is going to happen is that not only should pi be in the linear span of some pj, pk, pl, but pi will need to be in the linear span of many triples of columns which span it. So that in spite of corruptions, the decoder can find one which will accurately decode to the right answer. So the geometric translation of what it means to be a locally correctable code is the following. So you can look at this generator matrix, and you can look at the columns of the generator matrix and identify them as vectors in whatever field you're working in. So there'll be n points in f to the k. And if you wanted to decode to the ith location, you needed many of these vectors to linearly decode the ith location. This will correspond to, for every point pi, there should be many disjoint q tuples which span pi. So when q is 3, for instance, for every coordinate I, you need to have a lot of three-dimensional planes, or you need to have a lot of two-dimensional planes. So you have a lot of 3 tuples where you look at the plane through them, it must pass through pi. So you'll have all these 4 tuples containing pi, which are all linearly dependent. And this must happen for every coordinate. So so you take another point pj, and you'll have again many disjoint q tuples or 3 tuples which span that point. Okay, so that's the equivalent geometric translation. And notice that when these q tuples, for q equal to 2, this is exactly equivalent to the notion of being a delta Sylvester-Gallai configuration. For every point, there were many pairs of points which were collinear with that point. Here, when q is 3, for every point, there are many disjoint triples of points which are coplanar with that point. So it's like the Sylvester-Gallai configuration, but one dimension higher. So yeah, so they have n different matchings of q tuples, each corresponding to which point they are decoding. Okay, so locally correctable codes have played a very central role in theoretical computer science, in program testing, the PCP theorem, IP equals P space, etc. So they're a very fundamental notion, very well studied, but we still understand very, very little about what locally correctable codes we can construct and what is possible, what is not possible. So basically the only examples of locally correctable codes we know are the Hadamard code and the Reed-Muller code. And on the lower bound side, we only know very, very weak lower bounds for these codes. And it was shown by Dwyer that even if you want to talk about locally correctable codes when q is something as large as polylog q, even very weak lower bounds for these codes would imply new lower bounds in matrix rigidity. So they're interesting even with that connection. So let me tell you what we do know about what kinds of locally correctable codes we can construct and what lower bounds we have. So in the setting of 2 query locally correctable codes, the only example we know, the only constructions we know are the Hadamard code. And actually we understand 2 query locally correctable codes pretty well. So we do know that basically this is the only example of locally correctable codes we could have. So over F2, it's known that n needs to be at least 2 to the omega k, which is what the Hadamard code gives. Over Fp, it needs to be, where p is the characteristic of the underlying field, we know that these codes need to be of size at least p to the k. And this work by Barak, Dwyer, Vigdisson, and Yehudayov showed that over the real numbers, they just can't exist at all. At the moment we go to 3 query codes, what we know much less of what is possible. So the best upper bounds are the Reed-Muller codes, where n turns out to be 2 to the square root k. So k was the dimension of the set of points, n was the number of points. So the Reed-Muller code gives an example of a 3 query LCC where n is exponential in k, n is something like 2 to the square root k, and this is over, again, small finite fields. And over the reals we have absolutely no examples of such configurations of points where k is growing with n. So of course if you put all points on a line, then it is a 3 query LCC, but with growing dimension there are completely no examples. The best low bounds, on the other hand, so what is the best, so you want to rule out constructions of LCCs. For 3 query LCCs, the best low bound we have is actually much worse. So over any field, we know that n needs to be at least k square. So the dimension is at most square root of n. So k is at most square root of n. This is the best which we know, which is really far from the 2 to the square root k bound. And in a very recent new result with Dwyer and Vigdisson, over the real numbers, we get a very modest improvement over what the best is known. So we knew that n needs to be at least k square. What we now show is that n needs to be at least k to the 2 plus epsilon. So the k square was a kind of barrier to many proof techniques, and a lot of proofs seem to break down at this same n needs to be at least k square, and over the real numbers we are able to get a slight improvement. We can show n is at least k to the 2 plus epsilon, where epsilon is something like 1 over 1000. And and that's what I will spend the rest of the talk discussing, some ideas and what goes into this proof. So I think this is a really good place to make improvements, because they're very related to all the Sylvester-Gallai configurations and techniques, and we understand a lot about it, but the moment we went to higher dimensions, suddenly our understanding seems to be breaking down. Okay, so here's the geometric question, the underlying geometric question for 3 query locally correctable codes. Again, you have n points in some k-dimensional Euclidean space, and you know that for every point pi, there are delta n. Think of delta to be something like 1 over 100. So there are delta n disjoint triples, all which span that point. Okay, so take another point, and then there are some other delta n triples which span that point. So that's how the configuration looks. Again, the best earlier bounds showed that if you have such a configuration of points with this property, then k needs to be smaller than root n. N was the number of points, k was the dimension. And what we show in this work is that in fact k needs to be smaller than n to the 0.499. So we get a slightly better upper bound in the dimension. But we don't know, but this bound we have still might be really far from optimal. For all we know, any such configuration can only exist in constant dimensions when delta is a constant. Okay, so though we get some improvement, we really still understand very little about the structure of these points. Okay, so let me tell you some ideas in how we prove our result. So I want to show that k is less than n to the 0.499. As a warm-up, let me just first show why k is smaller than root n or root n polylog n. So in this warm-up already we'll see some ideas which will be as ingredients in our final proof. So you have a bunch of points, and you know that for every point there are all these disjoint 3 tuples spanning it. Here is the main idea. Okay, so let's take this configuration of points, and if possible it's in pretty high dimensions, something much more than root n. Let's pick some square root n points in our point set and map them to 0. So we'll find some linear transformation which puts these points in the kernel of that transformation and sends it to 0. So we'll pick square root n points and set it to 0. So what happens when we do that? you have about n different triples, these 3 tuples, and you're going to send square root n points to 0. This will tell you, so what is that with pretty good probability, in one of these triples, you hit 2 points in your square root, from among your square root n points. Because in each triple, the probability that you get 2 points is 1 over n, and you have about n triples. So, okay, when you set square root n points to 0, the dimension of your space reduces by square root n, and with the good probability for many PIs, some triple in the matching corresponding to that PI becomes a singleton point. Right? So if you have a triple where 2 of the points get set to 0, only 1 point remains, and that 1 point, so that was the 1 point which remained. There's a triple where 2 points get sent to 0, 1 point remains, and that 1 point must continue spanning PI. If the triple spans PI, after this transformation, the triple still spans PI, but 2 points went to 0. So what happens is PI got identified with that point. The only way 1 point spans another, they're basically the same point. So PI got identified with it. And you can do this and there was nothing special about that point. This is true for every point in your set. There was this matching. When you send square root n points to 0, PI got identified with some point. So what happens when you do this, basically the set just shrank by a constant factor, because most points got identified with some other points. So the number of distinct points just went down. Now if you do this entire thing carefully enough, you can see that you can actually iterate this process. It will shrink by a constant factor. You set another square root n points, it will shrink by another constant factor, and by repeating it log n times, you basically make the whole set shrink to only constantly many points, and hence the original set of points must have been in square root n log n dimensions. So you just set square root n points to 0 log n times, and the whole set just vanished. And that's basically the proof of the square root n bound. Perhaps one could hope that to improve this argument, maybe instead of setting square root n points to 0, you can do something more efficiently. Instead of random points, maybe carefully, cleverly choose points to set to 0. But in general, if you know nothing about the structure of these triples, if these triples are somewhat randomly arranged, then this kind of random restriction kind of argument, there's not much hope in improving. So this analysis is pretty tight. But what we show in our result, the way we get this improved 0.499, is to show that, okay, suppose the dimension is pretty large. It's more than n to the 0.499. Then we show that these triples, these different triples which decode every point, they are not actually arbitrarily arranged. There must be a lot of structure within the triples. So that's the first major component, that these triples, there's a structure theorem for these triples. In the second component, once you know that these triples are very structured, now you can perhaps go back and improve the random restriction argument to get better bounds. And that's what we do. So we'll first show that if the dimension is high, you get a lot of structure, and then exploit the structure to improve the random restriction argument. So let me tell you what the structure theorem is. We show that if the dimension is pretty large, then these points cannot be arbitrarily placed. These n points must actually break up into roughly square root n clusters, each of roughly square root n size. These will actually be square root n clusters of square root n points, and all these clusters will be roughly orthogonal to each other. But this geometric placement of the clusters is not important for us. The interesting property we'll also be able to deduce is that after you find these clusters, square root n clusters of roughly square root n points, the triples in your matchings are not going to be 1 point per cluster. The triples are going to be very special. For every triple, 2 of the points in the triple must be in the same cluster. So your triples will be either 2 in one cluster and 1 in another cluster, or all 3 in the same cluster. This is most of the triples are going to be of this form. So now, and once you have such a structure for the triples. And so these triples are basically very far from random. If you had a random collection of triples, then you would have triples coming from different clusters, most of the triples. And once you have the structure theorem, I'll show how we can get an improved random restriction. First, let me tell you why such a structure theorem might be possible. And so the main ingredient of our proof is this very beautiful result from convex geometry by Barth. And this is a very nice statement, just independent of the result I'm talking about, and might be useful elsewhere as well. And this result says the following. Okay, suppose you have n points in k-dimensional Euclidean space. And suppose you know that these points are nice in the sense that no large subset of points is in much lower dimension than the ambient dimension. So these points are somehow nicely distributed. Then you can somehow find a transformation for these points. You can find an invertible linear transformation which you can apply to these points. So you apply this invertible linear transformation and then you scale the points down to become unit points. Okay, so let's do that. There exists an invertible linear transformation M, so that for the new point pi prime, which is M times pi, and then normalized to become unit vectors, these new points are in some sense isotropic. In this precise sense, look at the new points. Then for every other unit vector W, if you look at the sum of inner products of W with all these pi primes, this quantity is small. It's at most n over k, which is roughly n over 0.501. And this bound is what you would get if these points were all randomly placed. So in particular, one consequence of this bound is that with you can't have too many, for every unit vector, you can't have too many points correlating with that unit vector. So you can have at most something like square root n points having any non-trivial correlation with that unit vector. So this transformation really spreads out the points nicely.
Is there any dependence on k besides the one you wrote?
No. So I've hidden what you mean by large subset in low dimension, right? So, and I've put an approximately n here. So I'm being a little fuzzy about the constants. If there's no large subset in low dimensions, then for most of the points, you might have to prune the set out by a bit, and then you'll have this property. And by large subset, I mean there's no n over 100 points sitting in n over 1000 dimensions, or k over 1000. So there's some play of constants going on. Then you can prune out your set by a bit, so that most of your points will then satisfy this. And the O will just have constants depending on the large subset low dimension, whatever constants you had there. So this is a very nice result. So basically what the consequence is that no one point will correlate with too many other points. Good. And the crucial point is this transformation preserves the property of being a locally correctable code. So if you had n points which had this 3-query LCC property of all these spanning triples, applying a linear transformation and scaling doesn't affect that property of being an LCC. So we can, without loss of generality, kind of assume we are in this situation where the points are all well spread out. Because if you have a large subset in low dimensions, then you will win for other reasons. So we can reduce to the case where all our points are nicely spread out and no one point correlates with too many other points. Okay. On the other hand, if you have a 3-query LCC, it's easy to see that you must have many correlated pairs of points. This is because whenever you have 3 points, a triple spanning a 4th point, so you have 4 points which are linearly dependent. The moment you have 4 points which are linearly dependent, some pair of points within those 4 points will have non-trivial correlation. So the fact that you are an LCC means there are many correlated pairs. This result by Barth tells you that these points are all spread out. So basically the only way to reconcile both these notions of points being spread out as well as having many correlated pairs is the structure theorem we mentioned. So that it takes some effort to actually get to the structure theorem from those two theorems, but they're the starting points, the fact that you have many correlated pairs and the result by Barth. And if you taken together, we're able to show such a clustering. Roughly square root n points in roughly square root n clusters, square root n points each, and the triples, every triple intersects some cluster in 2 points. So that's the clustering we deduce. And now let's see why, given such a clustering, we get the random restriction. So this is basically the last slide of the argument, and then I'll wrap up. Yeah. Okay, so now since the clusters, these triples intersect these clusters heavily, a lot of action is happening within the clusters, and not much is happening between the clusters in some sense. And if you just look at the structure more carefully, you will see that for every point, you have roughly n triples decoding it. Each of these triples must intersect some cluster. It's not hard to deduce that basically there'll be square root n triples intersecting cluster 1, square root n triples intersecting cluster 2, and so on and so forth. So now what we'll do is, instead of sending square root n points at random to 0 from the whole set, we'll pick one of the clusters and send just 4th root of n points to 0 within that cluster. Pick one cluster at random, send n to the 1/4 points within that cluster to 0, and then all the same consequences as before will hold. Dimension will reduce by only n to the 1/4 this time, but if you just look at it carefully, the structure theorem will just tell you that what properties we had before will continue to hold. For every pi, some triple will get intersected in 2 points, pi will get identified with some point, and the size of the set will shrink by a constant factor. And then you can repeat it log n times, and you can go down, and that's how you get your improvement. Okay, so that's basically the idea of the proof. Let me just summarize what we've seen. So we saw several variations of the Sylvester-Gallai theorem, and they were all of the flavor that if you have many local linear dependencies, then they imply some global bound on the dimension of the set of points. And these are very similar to the Feynman-Ruja kind of theorems in additive combinatorics, where you know that if you have a set of A with many additive triples within it, then the set of points must have a lot of structure or be low dimensional. And in fact, a lot of the lower bounds for 2-query locally correctable codes over F2 and Fp can be proved using additive combinatorics techniques over small fields. So there's a lot of parallels between both these worlds, and it would be interesting to see if you can use tools from here to talk about linear dependencies instead of additive dependencies. Okay, so and the setting we understand really very little is the high dimensional version, which is interesting for LCCs. So some of the questions which I talked about, which we don't know how to answer, so these results were very specific to the real numbers. It will be very interesting to get improved lower bounds for 3-query LCCs over F2, for instance. And this entire random restriction argument, that part of it still works. It's only the Barth part where we argue that the triples must be very structured, which we don't know how to make work. So, but perhaps this clustering is still true over F2. All LCCs must be very structured. Of course, showing much stronger lower bounds than the ones we show is a very nice question. It's also very interesting to so these were lower bounds for 3-query LCCs, getting improved lower bounds for more queries. So many of the ideas again would still work. So all everything we talked about, Barth and correlations, etc., still hold to be true. But in this case, the random restriction part right now is breaking down for more queries, and so we need to see how to get over that. And if you can get better lower bounds for more queries, this is very connected to the matrix rigidity problem, which I also mentioned. The stable Sylvester-Gallai is also a great question, which we have some bounds, but they're not optimal, and it would be great to improve them. So I'll stop here. So, thanks.
Any question?
Yeah.
Shachar. So, what type of dimension do you think the structure theory might still hold? So you prove that the structure theorem holds if the dimension is close enough to root n. But how do you know when it breaks?
So it's a bit fuzzy. So we say that if the dimension is at most n to the 0.499, then the kind of structure we get is that I said square root n triples with square root n clusters, but these clusters will have size n to the half plus minus epsilon. The number of points is also plus minus. So they all depend on the gap from square root n that the dimension had. So you might be able to get it down a little bit, but nothing significant. You won't be able to make the n to the half into an n to the 1/4.
But it can go to n to the 1/3, maybe. I mean, it's
Yeah,
not-
maybe n to the
it's not
1/3. You might be able to
always
come down significantly from n to the half to n to the 1/3, but you won't hope to go all. At least these ideas won't get you all the way down to something much stronger. But modest improvements, there's a lot of scope for, and maybe already what we do might give an improved structure theorem, but then the random restriction would hurt. So whatever constants we get kind of balances out both together. We suffered a little bit in the structure theorem and got strong random restriction. There we got much better improved bounds. We get only n to the 1/4 loss in the dimension instead of n to the half. So the random restriction part turned out to be very efficient here, but the structure theorem I was lossy in. But if you balance it out.
Can you hope to get a structure inside the cluster?
Great question. I don't know. Perhaps these are all so very, very structured. It's just how do you deduce the structure is what. It must be structured.
There are no such codes, so we
Yeah.
don't exist.
Is there a nice way of generating, maybe approximately, generating configurations with prescribed incidence parameters at random?
What do you mean by easiness?
Well, I mean,
parameters?
for example, you want to have a configuration of points, but with, say, such that for every point you have delta n triples. Basically for
Right. So we know actually very few examples. So I said delta. The only examples of delta Sylvester-Gallai configurations we have are basically these grids or a lot of different lines with all these points on it. We know very few examples. So here we're just capping the dimension of these points, but it might be true that not only is the dimension small, the set must look like this very specific set, and that we don't know how to show.
Okay. Thank you very much.